Good day everyone. Today we are going to be discussing about the Bernoulli's energy theorem. The Bernoulli's energy theorem. Applying the law of conservation of energy to fluids that may be considered incompressible, Bernoulli's theorem may be stated as: neglecting head loss, the total amount of energy per unit weight is constant at any point in the path of flow. Kinetic energy and potential energy. Energy is defined as the ability to do work. Both energy are measured in Newton meter or pounds-foot in English. Kinetic energy and potential energy are two commonly recognized forms of energy. In a flowing fluid, potential energy may in turn be subdivided into energy due to position or elevation above a given datum, and energy due to pressure in the fluid. Head is the amount of energy per Newton or per pound of fluid. So now let us talk about the kinetic energy and the velocity head. Kinetic energy is the ability of a mass to do work by virtue of its velocity. We can say that the kinetic energy is equal to weight multiplied to v squared over 2g. Therefore, the velocity head is equal to kinetic energy over the weight, or equal to v squared over 2g, as you can see on the screen. Potential energy may be subdivided into energy due to position or elevation above a given datum and energy due to pressure in the fluid. Elevation energy or elevation head is manifested in a fluid by virtue of its position or elevation with respect to a horizontal datum plane, which is equal to Z, as you can see on the screen. The pressure energy and pressure head is a form of potential energy. A mass of fluid acquires pressure energy when it is in contact with other masses having form of energy. Pressure energy, therefore, is an energy transmitted to fluid by another mass that possesses some energy. And the pressure head is equal to the pressure energy over the weight. Therefore, the pressure head is equal to pressure over the unit weight of the fluid. The total energy of flow. The total energy or head in a fluid is the sum of kinetic and potential energies. Recall that potential energy are pressure energy and elevation energy. Therefore, the total energy is equal to the kinetic energy, pressure energy, and elevation energy. And the total head is equal to the velocity head, the pressure head, and the elevation head, as you can see on our screen. So, the energy is now equal to v squared over 2g, in which it is the velocity head, plus the pressure head, in which it is P1, or pressure over unit weight of water at the point of consideration, plus Z. It is the elevation head in reference to the datum of our consideration. Here, number 1. Neglecting friction, the total head or total amount of energy per unit weight is the same at every point in the path flow, represented by this equation that from our figure, this is point 1 and this is point 2. So here is our reference datum. Now, v1 squared over 2g, in which v is the velocity of the fluid at point 1, v1, and g is the gravity. So that's, and then P1 over unit weight of water, since our fluid is water in our consideration. So here, this P1 is the pressure at point 1. And Z1 is the elevation head from our reference datum, equal to the energy at point 2 without. So here, there is no head loss. So V2 is the velocity at point 2 of our fluid, and P2 is the pressure at the point 2 in which we are considering, and Z2 is the elevation head from the datum up to the point of our consideration. The units of our heads are in meter. Next, number 2. Here is number 2. With continuous steady flow, take note, with continuous steady flow, the total head at any point in a stream is equal to the total head at any point in the downstream plus the head loss between 2 points. So in this equation, we are now considering the head loss. So, or the energy that was lost from point 1 to point 2, maybe due to friction, contraction, and much more. Since the Bernoulli's theorem states that the energy at point 1 is equal to energy at point 2, so to balance the equation, we will put the head loss here because some energy may be lost from point 1 to point 2. So, same again. So, V1 is the velocity at point 1. Here is our velocity head, the pressure head, and the elevation head. Same on the point 2. Velocity head, pressure head, and the elevation head. Plus the head loss, or the energy loss from point 1 to point 2 with the flow of our fluid. So, V1 is the velocity at point 1, P1 is the pressure at point 1, Z1 is the elevation head from our reference datum at point 1. Next, on the other side, the point 2, P2 is the velocity at point 2, P2 is the pressure at point 2, plus Z2, in which Z2 is the elevation from point 2 to our datum, plus the head loss. Okay, next, number 3, and number 3, this is number 3, sorry. And now, if we are going to place a pump or a turbine in between point 1 and point 2, our equation may be different because of the effect of the pump or turbine, as you can see here. So, with pump, if this is a pump here, if this is a pump, then our equation will be V1 squared over 2G plus P1 over unit weight of water plus Z1 plus the energy of the pump and caused by the pump, or E sub P, is equal to V2 squared over 2G plus P2 over unit weight of water plus Z2 plus the head loss. Okay, so you can see from our equation, the cost of the pump is to add energy from point 1 to point 2. And then if we assume that if we place a turbine in between point 1 and point 2, the equation now will be V1 squared over 2G plus P1 over unit weight of water plus Z1 minus E sub T, or the energy of the turbine. So, is equal to V squared, V sub 2 squared over 2G plus P2 over unit weight of water plus Z2 plus the head loss. So, let's proceed here. So, to further understand why is the energy of turbine and energy of the pump differs, let us look at how the pump or turbine affect the flow of water. Here in our equation, let us look at point A and point B. Yan. Let's assume that there is a pump in between point A and point B. If the flow of fluid is from point B to point A, the purpose of the pump is to elevate the supply and to add energy. And if the flow of water is from point A to point B, the pump will cause to increase the flow. Okay. Now, if it is a turbine in between point A and point B, the purpose of the turbine will be to remove energy. So that's why, as you can see, there is a minus sign on the energy of turbine. Now, let's see. So, power, if we are going to convert the energy, in which it is in meters that we have computed from the Bernoulli's energy theorem, we can convert it into power by using this equation, that power is equal to the unit weight of your fluid, so it may be water or it may be something else depending on the problem, multiplied to the Q or the discharge, multiplied to the E or the energy. So E is to be based on the Bernoulli's energy theorem. So the unit of power will be in kilowatts or joules per second, or Newton multiplied to meter over seconds. So 1 horsepower is equal to 0.746 kilowatts or 550 pound-feet per second. So to compute for the efficiency is just equal to the output over the input. So multiply to 100% to express your answer in percentage. Okay. Now next is the equation of continuity. Now, by the principle of conservation of mass, continuous flow occurs when, at any time, the discharge Q at every section of the stream is the same. So, continuity equation for incompressible fluids, take note, if this is an incompressible fluids, therefore, the density at point 1 is also equal to the density at point 2, meaning the fluid is the same from point 1 to point 2. Okay. The continuity equation will be A1 multiplied to V1 is equal to A2 multiplied to V2. So A1 is the air. Here, this is point 1 and here is point 2. So A1 is the area or the cross-sectional area of our pipe or in which the water flows. And V1 is the velocity of that fluid. Next, A2 again is the area at point 2 in which the fluid flows, and V2 is the velocity of that fluid. Now, where did the equation of continuity came from? It is assumed on, if this is point 1, let's assume this is Q sub 1 or the discharge at point 1. And this is Q sub 2 or the discharge at point 2. The discharge at point 1, which is Q sub 1, is assumed to be equal to Q sub 2. So, what goes into point 1 will go out to point 2. So, that's the continuity equation, in which the formula for the discharge is equal to the area multiplied to the velocity. So, the area is expressed, let's say, in meter squared. Multiplied to the velocity. Velocity is in meter per second. So, the unit of the discharge or the flow is equal to cubic meter per second. So, we can see that the discharge Q is also equal to the volume over the time. Yan. So, discharge is the amount of flow or water that flows in the pipe over a specific time. So, it is also equal to cubic meter per second. Okay. Now, what if your fluid is not an incompressible fluid? So, ibig sabihin, if it is not incompressible, therefore, the density at point 1 is not equal to point 2. Therefore, maglalagay lang tayo dito ng rho 1 and rho 2. So, that's the equation of continuity. So, this will be for the formula for the compressible fluids.